Buenas tardes a todos. Bienvenidos a un nuevo evento del capítulo regional Spanish Speaking Acousticians in the Americas. Somos un capítulo regional de la Acoustical Society of America. Em, Perdón. Bueno, esta introducción la hacemos en todos los eventos, pero para los que ya la escucharon, bueno, tengan un poco de paciencia, y para los nuevos les queremos comentar un par de cosas. La misión de este capítulo regional es simplemente conectar a los acústicos e interesados en el sonido y el audio que viven principalmente en las zonas geográficas de América Latina con la sociedad madre, que es la Acoustical Society of America, que es la sociedad científica de acústica más grande del mundo. Y lo que hacemos es desarrollar y divulgar actividades que son de interés para nuestros miembros. Hoy por hoy tenemos una muy importante membresía distribuida geográficamente en todo el mundo. Tenemos 329 miembros repartidos en 4 continentes y en 30 países, siendo los países con mayor cantidad de miembros Colombia, México y Estados Unidos. 49 de nuestros miembros son miembros de la Acoustical Society of America y están repartidos en 14 áreas técnicas. O sea, ustedes saben que la acústica es una ciencia muy interdisciplinaria y tenemos 14 áreas técnicas que van desde la acústica arquitectónica hasta la acústica submarina y otras áreas de incumbencia de la acústica. 97 de nuestros miembros son estudiantes y siempre, bueno, le damos la bienvenida a los estudiantes que se quieran sumar. Bueno, si ustedes me preguntan cómo se pueden unir al capítulo, bueno, simplemente hay que entrar al link que está ahí arriba y apretar, llenar los datos y apretar únete. No hay que pagar nada, es totalmente gratuito. Pero si están interesados en participar en el capítulo, en la organización del capítulo, pueden enviarnos un email. Esta participación en la junta directiva del capítulo es voluntaria, no es un cargo ad honorem, no hay un pago y requiere una cierta responsabilidad y cumplir con ciertas tareas, ¿eh? Si quisiesen unirse y no lo hicieron a la Acoustical Society of America, hay distintas maneras de hacerlo. Hay una nueva categoría que se llama CA Associate, que es para personas de países en desarrollo, que incluye todos los países de habla hispánica, y el precio es bastante reducido, es de $50 por año. Después, para los estudiantes, hay una categoría especial que uno puede ser miembro por $50 por año. Ser un full member que permite, entre otras cosas, votar en las elecciones de la Acoustical Society of America cuesta $200 por año. Y hay una categoría que se llama Associate Member, que tiene los mismos beneficios que un full member, pero sin derecho a voto. Y se pagan $150 por los primeros 5 años y después uno pasa a la categoría de full member, siendo $200 por año el costo. Esta es nuestra junta directiva. Los que están en la fila de arriba son cargos específicos que tienen tareas específicas que realizar. Los que estamos abajo somos los Member at Large, que colaboramos con el capítulo, pero no tenemos tantas tareas específicas. Y como les dije, si se quieren sumar, son bienvenidos. Implica una cierta demanda de tiempo y de responsabilidad. Pero siempre le damos la bienvenida a nueva gente que se quiera sumar. Estas son nuestras redes por las cuales nos pueden seguir. Todos los eventos que nosotros realizamos se graban y están en nuestro canal de YouTube, tanto en inglés como en español. Y estas son nuestras redes sociales. Well, I will now switch to English, and today I'm presenting Dr. Megan Ballard, and she will give us a presentation called Using Acoustic Remote Sensing to Monitor the Carbon Cycle in a Seagrass Meadow. So I've known Dr. Ballard from Penn State. She was pursuing her PhD there, and I was doing my master's, and back in 2005, more or less. So nowadays, Megan is a research scientist at the Applied Research Laboratories at the University of Texas at Austin, and she received her Bachelor of Science in Ocean Engineering from Florida Atlantic University in 2005, and her PhD in acoustics from Penn State in 2009. I think you were at the top of the class, weren't you, Megan?
I don't know.
Yes, I think so. Uh, Dr. Ballard's research areas are related to underwater acoustic propagation modeling, geoacoustic inversion, and direct measurement of marine sediment properties. She received numerous awards and recognitions, for example, the Wood Medal from the Institute of Acoustics in 2021, the Bruce Lindsay Award from the Acoustical Society of America in 2016, the Postdoctoral Special Research Award from the Office of Naval Research in 2011, and the National Defense Science and Engineering Graduate Fellowship Award in 2006. Dr. Ballard is a fellow of the Acoustical Society of America, the past chair of the Technical Committee on Underwater Acoustics at the Acoustical Society of America, and the current editor of the Proceedings of Meetings on Acoustics. Well, I will stop sharing my screen and I will let Megan, give her presentation today. Thank you very much.
Okay, thank you so much, Fernando. And let me get my slides up. Oh. Okay, so thank you, Fernando, for the excellent introduction. As Fernando told you, I'm a research scientist at the Applied Research Laboratories at the University of Texas at Austin. And I'm showing a picture here. This is myself on a sea experiment. And this is actually the homepage of our lab right now. And I'm working to collect some direct measurements of acoustic propagation around the pancake ice that you see in this photograph here. I do have a blog, and I can show you that on this slide here. It's the address is arlinthearctic.wordpress.com, and I just wanted to show this to you. It has a lot of outreach about different oceanographic experiments I've done, and a lot of this work is collaborations with other people from my own lab as well as researchers from other universities. And so this is kind of a fun way to look at things, and it has a lot of great pictures on it. The thing I'm going to talk to you about today is called a 2-year record of acoustic remote sensing in a seagrass meadow. And this is a collaboration with Kevin Lee, Kyle Capistrafasa, who's a graduate student, Andrew McNeese, who's an engineer in our group, and Colby Cushing, Thomas Jerome, and Rob Taylor are all postdocs. Preston Wilson is a professor of mechanical engineering, and Ken Dutton is a professor of marine science, both at the University of Texas at Austin. And this work is sponsored by the Office of Naval Research, the National Science Foundation, the Texas General Land Office, and the two logos on the right are of the Marine Science Institute, who we've worked closely with on this project, and then that of my own lab, the Applied Research Laboratories at the University of Texas at Austin. So we're using acoustics to study seagrass. So you may be wondering why we're so interested in seagrasses. So seagrass ecosystems provide a multitude of services, and they also serve as important blue carbon stores. However, seagrass habitats are among the most threatened ecosystems on Earth. And so we're seeking long-term and continuous measurements of seagrass parameters, and this can be used for ecosystem health assessment and sustainable management. So now that I told you why seagrasses are important, you may wonder why we use acoustic methods to assess and monitor seagrass. So the conventional measurements in seagrass meadows are made with dissolved oxygen sensors, and these are chemical sensors. They're most widely used. However, when the water is saturated with oxygen, free gas bubbles are formed, and the free gas is not measured by the chemical sensors. On the other hand, acoustic signals are very sensitive to the presence of bubbles, which cause dispersion, absorption of scattering and sound. And there's both gas bodies within the seagrass tissue, as well as bubbles that freely float in the water. So I wanted to tell you a little bit of work about the history of acoustic sensing of photosynthesis in seagrass. And the initial work was conducted by J.P. Hermand in the late 90s and early 2000s. And he concentrated on Posidonia, which is a Mediterranean species of seagrass. This is a unique species of seagrass, and it has a thick mat of interlaced roots and rhizomes that entangle carbon within the sediment. J.P. Herman's principal result was his experiment proved unequivocally that the significant variations in the acoustic waveguide propagation characteristics, namely the attenuation and the time dispersion, were due to bubbles of photosynthetic oxygen produced by the seagrasses. Later, Philip Berto also worked on Posidonia and then another Mediterranean species known as C. meadosia. He collected a number of experimental measurements, and he found that the significant production of oxygen bubbles produced by seagrass ecosystems suggests that net primary production is underestimated by methods that rely on the mass balance of dissolved O2 measurements alone. Work has also been done in Asia. This is work on C. meadow rotunda, which is an intertidal species of seagrass, meaning that the seagrasses are sometimes underwater and other times they're exposed to the atmosphere. This data was collected in the Dangsha Atoll, and they found individual bubble residences in the gas content of seagrass meadows, and they saw more than 40 dB in the diurnal variations of mid-frequency propagation loss. Now moving on to some of our own work. We've concentrated on species in the Gulf of Mexico, and the species that we've studied the most is the Thalassia testudinum, and our initial work was done in the lower Laguna Madre. We used a really wide band of acoustic excitation spanning from 1 to 100 kilohertz, and that allowed us to identify the excess attenuation occurred between 3.5 and 35 kilohertz. And we saw the most attenuation when bubble production was at a maximum in the afternoon each day. We also made comparison measurements in a nearby bare patch of sediment, and we saw more than 40 dB in reduction comparing the bare patch to the vegetated site, and then another 10 to 15 dB of loss when photosynthesis was at a maximum in the afternoon each day. We also looked at seasonal variation in the meadow. So in this case, we had hydrophones that were cabled back to shore. The left plot shows data collected in February. There's about 3 days of data there. And then the right plot shows data collected in September, which is one of the warmest parts of the year here in Texas. And you can see there's much larger variations in the received energy level. That's this middle plot shown here. There's 4 colored lines here for the source that was 1.5, receivers that were 1.5, 3, 6, and 12 meters from the source. And then in the bottom plot, you can see the frequency dependence of the received level. And the highest loss, that's that area where the darkest blue is, occurs when we have the most sunlight in the middle of the day, which is also the time period when the dissolved oxygen is the highest. We also did an experiment in a Thalassia meadow where we used a Bayesian inference to attempt to determine the void fraction of seagrass present in the area. This used a model for free bubbles, and it incorporated both the bubbles that were produced by photosynthesis and floating freely in the water, as well as the loss of due to gas channels constrained within the seagrass leaves. So this initial work compared propagation in the seagrass meadow to propagation in a nearby bare patch, which was sparsely vegetated with seagrass. So here the light blue line is that area that had much less seagrass and has a smaller void fraction of gas present. And then we did 5 repeated experiments during the day in the seagrass meadow. And here we have much higher void fraction. So we've demonstrated sensitivity to the gas present in the meadow. We've also done a number of laboratory measurements. Here we concentrated again on the Thalassia seagrass. These grasses are like a long ribbon, as you see in the picture on the left. And when you slice through them, making a cross section, you can see these gas channels, which are called the lacuna, which are inside the seagrass leaf itself. There's an epidermis on the outside of the leaf, which is a slightly thicker, more rigid material. And then around the lacuna, we have the parenchyma, which is a more acoustically compliant material. So between laboratory measurements conducted using an acoustic resonator, using mechanical analysis using a DMA, a dynamic mechanical analyzer, with finite element modeling, we're able to determine the shear modulus of the leaf as well as its compressional wave modulus. So building on all that work that had been done in the past, we developed this system to be in the field. We had it deployed for 2 years. There's an electronics pressure housing that controls signals that are emitted from the source, and then we record them on these 4 receivers. And you can see from my diagram, they're located about 1.5 to 12 meters away from the source. The average depth of this waveguide is about 1 meter, although it varies as the tide changes. And then we had the source broadcast chirps between 1 and 100 kilohertz. The transmissions were sent every 10 minutes throughout the day and night for 2 years. We also collected ambient sound data from the first 30 seconds of each recording before the transmission started. We collected environmental measurements, including water depth, temperature, and dissolved oxygen, and also atmospheric data, including solar irradiance. Our experiment site was on the Texas coast near Port Aransas, which is where the Marine Science Institute of the University of Texas is located. And I'm showing an aerial photo of our experimental site. This area is known as the East Flats part of Corpus Christi Bay. You can see some PVC poles in the figure. I'm outlining them here with my mouse, and they're over here too. There's 2 team members here working to deploy our acoustic measurement system. And then here you can see the boat where we move out from shore to service our acoustic system. We also collected cores. This guy near the boat is collecting a sediment core. We do that to have some ground truth measurements to compare with our acoustic data. It's just taking a closer look of the data we collected in the field. We made routine trips to service our acoustic system every 2 to 3 months. So we had 2 pressure housings here. One of these has the electronics, the other one's just filled with batteries. This powered our source, and we also have the recorder for the receivers. This is a dissolved oxygen sensor here. There's also a depth sensor attached to the system right here. And then the acoustic source and the hydrophones were detached from the recorder, and they were left in the field continuously for the 2-year period. We were typically able to clean this up, replace all the batteries, and download all the data within 24 to 48 hours. This is an example of a close-up of one of our salinity sensors. You can see the biofouling around the sensing element. So this is a really challenging environment to work in just because it's so biologically active. So this slide shows a summary of the 2 years of data that we collected. The top panels show a lot of the environmental measurements, and then moving to the bottom, I'll describe our acoustic results in more detail. I plotted the 2 years of data on top of each other. So we started our acoustic experiment in October of 2021, and that's this darkest green line that you see on the right. Then 2022 is the kind of mid-colored green, and that's plotted continuously for the entire annual period. And then 2023, we finished the experiment in mid-November, so the lightest green line stops there. I'm going to step through each of the measurements we collected one by one. So the top plot shows photosynthetic active radiation, which is known as PAR, and this is the wavelengths of sunlight that are used by plants for photosynthesis. And you can see from this we have more intense sunlight denoted by the higher amplitude. And I can tell you we also have longer days during the warmer months. Water temperature is shown on this plot. We have warmer temperatures from about April to November. Wind speed is shown here, and we have calmer conditions generally from May to October. Rainfall is shown here, and you can see the evidence of some storm events. So for example, here we have rainfall, and then you can see a drop in temperature and an increase in wind speed. Water depth is shown on this plot here. You can see it's kind of around a meter or a little bit less, and we do see seasonal variations in water depth, as well as a tidal variation, and it's also influenced by wind that can push water across this shallow bay. So dissolved oxygen measurements are shown on this plot here. Again, this is the amount of oxygen that's dissolved in the water and measured with the chemical sensor. And you can see the levels of dissolved oxygen build from through the spring, reach a maximum level in the warmer months, and then reduce to smaller reductions, fluctuations in the fall out here. And again, you can see the diurnal cycle in these dissolved oxygen measurements as well. So this is our transmission loss shown on this panel here. It's calculated from the pulse compressed signal recorded on the hydrophone. It says 6 meters. This was actually on this plot 1.5 meters away from the source. And then you can also see a diurnal pattern, which I've highlighted on. Oh, the diurnal pattern is the high frequency fluctuations that you see, and that's from the photosynthetic bubble production that causes increased transmission loss. It means the highest levels occurring during the warmer months when the seagrass is most productive. And then there's also a seasonal pattern, and you can see increased transmission loss in the nighttime hours when we don't have the bubble production. And this really follows the life cycle of the seagrass, which is most productive in the warmer months and becomes less productive in the cooler season. Ambient sound, the metric I'm showing on this plot is calculated from the 25th percentile level and then averaged over the 1 to 10 kilohertz band. We choose the 25th percentile level because that represents the background sound level and is not influenced by short clicks or short time loud events. Here you can also see the diurnal pattern. This is the signal associated with bubble production, because as the bubbles leave the seagrass leaves, they oscillate, and that there's enough of these small bubbles oscillating that it actually raises the level of ambient sound in this environment in afternoons, especially on warm days in the summer. And then finally, as I mentioned, we collected seagrass cores, and we used those to compute the above ground biomass. Above ground biomass is the leaf portion, and then below ground biomass would be the roots and rhizomes. And biomass is reported as the dry weight of the leaves collected. And we collected these using 15 centimeter cores. Here I'm just showing some photographs comparing the kind of more dormant season. So here you can see the plants are smaller, they're more spread out. You can see the sandy bottom in between them. And then if you compare that to September, which is the photograph on the right, you can see the seagrass meadow is much more dense. The leaves are much longer. They're about 30 centimeters or more in length in this picture. And the meadow is so dense you can no longer see the seabed in between. I want to take just a moment to take a close-up look so I can show you those diurnal changes that I mentioned. So here I'm showing a 1 week from data collected in May. And again, there's 2 years of data on here. We're seeing both 2022 and 2023. And I've highlighted the period where the dissolved oxygen surpasses 100%. And that's the time where we begin to see the increase in transmission loss, as well as the increase in the ambient sound level. And then when the dissolved oxygen passes below 100%, the transmission loss goes back down to its kind of overnight level when there's no bubble production going on. And then the ambient sound also goes back down to its sort of background level when there's no bubble production. Oh, that's what I just said. So those arrows are pointing out the timing of when we have that increased transmission loss in ambient sound. And again, that's aligned with the what's driving this is the sunlight, which is denoted by the PAR data in the top plot. I did want to point out a weather event here. This is kind of the non-example. So in this second day of the week in May, in the 2023 data, which is shown by the lighter green line, you can see that we don't get as much sunlight. And as a result, the dissolved oxygen does not surpass 100%. we don't get that increase in transmission loss, which is associated with the bubble production, or the diurnal increase in ambient sound, which is also what's associated with the bubble production. Oh, those arrows were just pointing out what I said. I also want to talk a little bit more about the ambient sound. So if you look at the background levels comparing 22, which is the darker green line, to 23, you can see in 2023, the overnight ambient sound levels are a little bit lower, and that's because the wind speed is a little bit lower. So overnight, we're really dominated by wind-driven ambient sound, whereas during the bubble production period, the bubbles are what's making the most sound. And you can see even on the windier year, during the afternoon, the bubble production is still the same as it is during the calmer conditions. And then you can also see a rain event here on that stormy day in 2023. You can see the peaks in the rain are really well correlated with the peaks we see in the ambient sound. So again, the sound of rain and the sound of wind are really well-known characteristics of the underwater soundscape for typical underwater environments. But what's unique here is we have the seagrass and we're hearing the sound of bubble production. So I showed you kind of all of the data at once, and this is just another way to look at our transmission loss, and then I'll show a similar plot for the ambient sound. So what I'm really getting at here now is the frequency dependence of the transmission loss, which we couldn't see on the other plot. And I've made monthly averages, so I've taken all 30 or 31 days from the month, from each month of the year, and then I've taken the median level for each of the 10-minute each 10-minute segment that we have, because we have recordings every 10 minutes. And then I've plotted it as a function of frequency between 1 kilohertz and 50 kilohertz. Even though I first mentioned that our chirp went all the way up to 100 kilohertz, we didn't have good signal to noise ratio above 50 kilohertz. So I've cut off this plot at 50 kilohertz because below that we can't detect, at higher frequencies we can't detect our signal. But you can clearly see here each day, especially in the, on average, especially in the summer, we have the greatest transmission loss occurring in the afternoon. This is UTC -5, which is local time at our site, when we have the most sunlight. The red line on here is the monthly average dissolved oxygen. So you can see when the dissolved oxygen surpasses 100%, that's when we really get this increase in transmission loss. And you can see we have the increases kind of going over a wider band and being more significant in the summer, but this peak frequency of transmission loss is consistently around about 10 to 12 kilohertz. The other thing you can see on here is if we look at the frequency dependence of the overnight transmission loss. So this is the transmission loss that we attribute to that increased amount of seagrass leaves that have grown throughout the year. And we can see that it occurs at slightly higher frequencies, which we would expect for bubbles that are constrained within the seagrass tissue. And you can see it follows the growth season. So when the seagrass leaves are biggest in the summer, we have the most transmission loss in this band. All right, so this is the same type of plot, but for the ambient sound data. And then the ambient sound data was most significant between 100 hertz and 20 kilohertz. So this is a lower frequency band than I showed you on the previous plot, just to help orient you. All the plots are still computed in the same manner, though. We've got the median level for every 10 minutes in each frequency band. And what I really want to draw your attention to is this increase in ambient sound that occurs when the dissolved oxygen level surpasses 100% each day. Another unique aspect of this data, I want to draw your attention to this like sloping decrease in ambient sound, which we see especially above 4 kilohertz. And this occurs because of increased transmission loss. And to help illustrate that to you, I've overlaid the transmission loss curves from the previous slide on these ambient sound data. So now you can see that this increase in transmission loss, if you can see my pointer, I'm trying to point out the month of May for you. We have decrease in ambient sound the same time, it's the bubbles that cause the ambient sound, but the presence of the bubbles is also causing this increase in transmission loss. So even though we have most bubbles in the afternoon when the dissolved oxygen level is really high, we also have more transmission loss during this period. So the overall ambient sound measurement decreases later in the afternoon. I'm also pointing out this other peak in transmission loss occurs around sunset each day in the spring, summer, and fall months. And this is the mating call of the spotted sea trout. And they just chorus most every day during this time period. And so we can clearly see them in our 25th percentile ambient sound as well. Okay, so now we've taken a look at all the data. We've seen the frequency dependence of the data using monthly averages. But is there something we can do to understand this large data set more holistically? So I've applied k-means clustering for this. If you're unfamiliar with k-means clustering, it's being demonstrated in the GIF on the right for a two-dimensional data set. And so you can see as it starts over right now, it's kind of randomized. You tell it, you expect there to be 4 different clusters of data. And you can see as it iterates through, you end up with all the dots kind of nearest these gray dots are the centroid being clustered together. So in this data set, I have the transmission loss and the ambient sound as a function of frequency. So the length of the vector that I'm using to cluster is the entire frequency spectra of the signal. And it's been normalized as a standard procedure for this type of automated or machine learning algorithm. So here I'm showing the results of the clustering analysis, and I said the transmission loss now is shown in this left panel of the figure on the right, and then the clusters for ambient sound are shown in the second panel, and then I'm just comparing it to some of the environmental measurements on the far right. The spectral shape, which is the centroid of the normalized ambient levels, are shown for the transmission loss and the ambient sound here on the left, and then the amount of transmission loss as a histogram for each of the elements in this cluster are shown in the bottom figure for first transmission loss and then ambient sound. So let me first describe to you what we're seeing in these transmission loss clusters. So this darker and lighter blue, these are attributed to the photosynthetic bubble production. So on this scale, you can see we're getting a lot more bubble production as we move into the warmer months, especially April. And then the highest level of bubble production is really this TL1, which is characterized by this largest peak here in the 10 to 12 kilohertz range. And we also see that in 2022. This cluster TL3 kind of fills in around the edges, and it's a little bit of a misnomer how it fills in the overnight time here. This could actually be due to some biofouling on our hydrophones. But we also have clusters TL5 and TL4. These are observed in the overnight hours when we don't have much bubble production going on. And we have 2 of them, one representing the dormant season when the seagrass are very small, and then the other one representing the productive season when the seagrasses are more lush. So we're propagating the signal through more seagrass, we get cluster TL4, and when the seagrass are largely absent, we get cluster TL5. Moving on to the ambient sound clusters here. Again, I have AS1 and AS2 representing the bubble production. They're very identifiable because of the time of day and time of year in which they're observed. That spotted sea trout, you can really see that it comes in here around sunset each day. And there's about 40% more spotted sea trout clusters in 2023 compared to 2022. This is kind of an interesting feature because we had a huge winter storm in 2021, which shut down a lot of the state of Texas. And there was a big freeze event on the coast that caused a lot of fish to die. So as kind of a bonus of the seagrass monitoring, we're actually seeing some recovery in the spotted sea trout population. And then Here you can see we've got AS4 and AS5. AS4 is observed during more of the windy conditions, whereas AS5 we see during calmer weather. I also want to point out how this type of analysis can be used to observe some episodic events. So if you can see these tiny red arrows on my plot, there's a time period here in the morning of 3 days in a row in September where we had clouds and rain for 3 consecutive days. And you can see that here in the lack of sunlight and the increase in rain. And so during that period, we don't see the increase in transmission loss, and we observe TL4 throughout most of the morning, and then we don't get that signature of the bubble production in the ambient sound either. Okay, so how can we use this data to do ecological purposes? So I've shown you in the past several slides, we're sensitive, acoustics are sensitive to both the biomass as well as the bubble production. And now on this next couple of slides, I want to tell you how we're using that for ecological purposes. So net ecosystem production is the difference between gross primary productivity and net ecosystem respiration. So it can be used to represent the total carbon in an ecosystem that is stored, exported, or oxidized back into carbon dioxide gas. And so here you can see the simple equation for net ecosystem production. It's equal to the gross primary productivity minus the respiration. So the production of oxygen generally occurs during the day, and then the use of oxygen or the respiration generally occurs overnight in this seagrass meadow. So the dissolved component of both gross primary production and respiration can be estimated from a rate of change of DO measurements. And this is what's conventionally done to estimate net ecosystem production in seagrass meadows. So the goal of this work is to use the non-dissolved contribution of oxygen, which is the bubbles that we're measuring acoustically, to estimate gross primary productivity. So we deployed these bubble traps like the one you see in the photograph on the left. The main components of this are the large collection funnel, which siphons gas into this gas collection chamber. And we're able to remotely monitor the amount of gas within the chamber using these two pressure sensors. There's a reference pressure sensor that just monitors the ambient pressure because we see changes in pressure due to waves as well as tidal changes. And then the trap on the left, which is connected to the gas chamber. By subtracting these two, we can get an estimate of the amount of gas in the chamber. So we can leave this out for a full day and get the diurnal cycle of gas collection. So we had 2 traps deployed on 27 September 2023. They're shown by the dashed and dotted lines, and then the mean of these two is shown by the blue solid line. And so we use this regression and comparing it both to the TL measurements during that period, as well as the ambient sound measurements shown in orange. And you can see there's good correlation in the timing of the kind of, we didn't get the onset of the bubble production, but we did get the reduction in both the ambient sound and transmission loss as they occur as the sun begins to set. So the equations for these regressions are written here. And so that we can then apply those to get an estimate of the amount of gas flux produced in the meadow from the bubbles. Okay, so first on the left, I'm showing you the estimate of the seagrass meadow using only the dissolved oxygen measurements. So this does not account for the gas evolution that we determine acoustically. And in this case, our meadow is heterotrophic. Heterotrophic means that carbon dioxide is being released to the atmosphere. And you can see that because we have a negative net ecosystem production. On the other hand, when we include the amount of gas from the bubbles, now you can see that the result is positive, especially in the summer here, and that's autotrophic. And now annually, on average, our meadow is sequestering carbon. I will say that there's 2 lines on here, the light and dark One of this is just a multivariate regression using the dissolved oxygen, water depth, temperature, all the environmental data. And then the lighter green dots and error bars, that is the acoustic derived metric. But both generally show that we've transitioned from heterotrophic, and then when we include contribution from free bubbles, our meadow is autotrophic. We can do similar regression for the amount of biomass present in the seagrass level. So here we've used kind of the background nighttime level, and we've done a regression using core data. The cores are shown for the above ground biomass are shown here on the right. And we only have cores from 2023, and then the regression is shown below. Here you can see one of those 15-centimeter cores. The process involves sieving away all the sediment. Then the leaf material is cleaned and brought back to the lab where it's dried in an oven and then weighed. Okay, so I actually have, this is kind of I have a few more slides after this. I'm going to tell you about some of our ongoing work, but I hope to show you in these slides that we're sensitive to the frequency dependence of the photosynthetic bubble production, as well as the seasonal changes in biomass. And then the combined analysis of transmission loss and ambient sound proved useful for interpreting the data, and especially meaning we see that reduction in the ambient sound when transmission loss is at a maximum. We have ongoing efforts to continue to analyze the data in the current in this data set. And instead of using the empirical regressions that I told you about, using the bubble traps or the core data, we really seek to use the Bayesian inference along with effective media models to estimate both the gas flux and the biomass. And then we'll be able to use those bubble trap and core data to ground truth what we're doing. And then I'll have a little bit about future work on my last slides. If you're unfamiliar with Bayesian inference, we take our meadow and then we'll parameterize it into a depth-dependent sound speed attenuation and density profile. Probably also have a sediment profile in the bottom. And as I mentioned, for the free bubbles, there's an existing model that was developed by Commander and Prosperetti in 1989. But for the seagrass tissue, we've been working with our group to develop a new model. So this model includes the shape of the lacunae, which are the gas channels, as well as the compliance of the parenchyma and the effect of the epidermis. The new models that we've sought, developed by Thomas Jerome, who's a postdoc in our group, he's developed two of these. One is known as the micromechanical spring mass damper model. You can see it's most similar kind of to the shape of our Thalassia leaf. He's also investigated a cylindrical seagrass model using multiple scattering theory. And this one's not as similar to our Thalassia leaf, but it does look quite similar to a syringodium leaf, which is this more cylindrical leaf that has the air channels within. These are the equations he came up with. I've listed the parameter values here. I'll say one unknown that was fit to some data that was collected. These were low frequency measurements collected on seagrass leaves by a graduate student that worked with us. And you can see they provide a very nice fit to the micromechanical model. But you know, this low frequency regime, we're away from kind of where a lot of the action is here at higher frequencies, where we see the dispersion in the sound speed and the increase in attenuation. So for that, our group has developed an artificial seagrass. This is done because the gas channels are all in uniform shape and the properties of the material can be controlled. So this was made using a 3D printer in our lab, and the material used in the printer is known as TPU, which is an expanding thermoplastic polyurethane. And then it was coated with a thin rubber waterproofing, which happily is kind of similar to the epidermis you would see on a natural seagrass leaf. So using this artificial seagrass leaves, we examine the higher frequency regime. This uses the same low frequency effective resonator measurements. Basically, this is looking at the modes within this glass cylinder here. There's some black things in here. These are the artificial seagrass leaves that have been coated with that waterproof rubber. There is some effects of the tube itself because it's glass and it has some acoustic compliance. So the phase speed measurements are here, but then you can back out the intrinsic sound speed. So on both of these plots, but not going into the details of the phase speed, looking at the intrinsic effective sound speed of what's in the tube, water will have a sound speed ratio of 1, and that's what's shown in black. And then the experiment was conducted twice with increasing number of seagrass leaves present. So the red decreases the effective sound speed, which we expect because we've introduced some gas entrained within these artificial seagrass leaves. And then when we double the number of leaves to 14, we can see that the effective sound speed is reduced further. The two models, the micromechanical model and the multi-scattering model, were fit to the 4 data points that are shown here. You can see that they fit well for these data points for both data sets. But then moving forward to examine this higher frequency range here between 10 kilohertz and a megahertz, we use this type of setup. The seagrass leaves were suspended. They float, so they're like suspended upward from a glass plate. They're suspended by some strings. This source that you see in the figure right here outputs a plane wave, and we can look at plane wave propagation through the field of seagrass leaves. And in this case, the hydrophone was scanned from the beginning of the artificial meadow to the end of the artificial meadow. This is the water only, the source only. This is the water measurement. So before the seagrass leaves were introduced, and when the seagrass leaves are introduced, you can see that the time series changes significantly. The experiment was conducted 3 times with 8, 16, and 24 leaves present. These are the final results for 24 samples, and the micromechanical and multi-scattering model were fit to both. The micromechanical model, which is the green dashed line, way overestimates the attenuation. And this is the waveform that was measured at the far end of the meadow. And you can see the micromechanical model is providing an excellent fit to the experimental measurement, which is shown by the solid blue line. And then again, the multi-scattering model, which is shown by the green dashed line, is overestimating the attenuation. Okay, I do feel like I'm running out of time, but I am near the end. I just wanted to show you some of the time series data we collected. The goal is to use the models that have been compared with the artificial seagrass, as well as the live seagrass in that low frequency range, and then apply them to measurements conducted in our meadow. So here I'm showing data from 2 different seasons. January 11 is shown on the left, August 11 is shown on the right, and then 2 times of day. We have kind of the overnight period where we have less loss, and then the midday where we have the most loss. And you can see the time series data shown on the bottom, where we're comparing the 2 times of day on the left in January, and then the 2 times of day on the right in August. And especially in August, you can see the bubble production causes a large increase in the transmission loss. Furthermore, I've kind of zoomed in here so you could see the signals. When I don't zoom in and I plot them on the same scale as January, you see that the time series is very much smaller. Then looking at the frequency spectra for the 2 years, you can see the increase in transmission loss caused by the free bubbles by comparing the blue and orange. And then you see the seasonal difference, 20 dB, and nighttime levels decrease due to the biomass, all those seagrass leaves, and then an additional 40 dB in the afternoon in the summer due to the bubble production. Okay, this is the very end, just a little bit about where we're going next with this. We have a new project funded by the Advanced Research Projects Energy. So this is, if you're familiar with DARPA, this is kind of the DARPA of energy. This program is focused on developing methods that can be used to quantify marine carbon removal techniques. So seagrass, planting seagrass meadows or restoring seagrass meadows is a nature-based solution for carbon dioxide removal, but how can you determine if a planted meadow is actually removing carbon from the atmosphere? So we're applying the acoustic techniques that I told you about for that. So we're developing an acoustic sensor network that will quantify ecosystem activity and how effective carbon is stored in shallow seagrass beds. And again, this is an important sink for the coastal blue carbon cycle. And this is my final slide. This is my team. Huge thanks to everyone who worked on this project with me, Ken Dutton and Kyle Capistrat-Fassa are the biologists who supported this work. And then Preston Wilson is professor of mechanical engineering, also involved in acoustics. And then Kevin Lee and Andrew McNeese are at the Applied Research Labs with me, as well as Colby Cushing, Thomas Jerome, and Rob Taylor, who are postdocs in our lab right now. So I just want to say thank you very much for listening to me, and I'm happy to answer any questions you might have.
Well, thank you very much, Megan, for this very interesting presentation and of your research, so valuable for so many reasons now. So I think it's really interesting. Hope we had more of that here in South America. So let's see if anyone has any questions that they can put it into the chat or the Q&A. I do have some questions, but I want to wait until other people provide some other questions. I see. Don't be shy. ¿Hay preguntas para Megan? ¿Alguien tiene una pregunta? Felipe, Ivonne, ¿tienen preguntas para Megan? ¿Algo que no se ha quedado claro? Bueno, yo tengo dos preguntas. I have two questions. And they're more based on some fundamentals that since I know very little about underwater sound, I wanted to ask you some fundamental questions. So why do oxygen bubbles absorb sound, or absorb or increase the transmission loss of sound? Is it due to some type of cavitation or something like that? What is the mechanism?
It's there's the bubbles oscillate when sound hits them, and they absorb sound, and they also scatter sound. So it's really absorption and scattering of sound is what causes the loss.
Okay. And the other thing is that I'm more used to room acoustics, and typically the high frequencies in sound in air are very much are very attenuated when in, for example, in a concert hall or something. So it's like the atmosphere is like a low pass frequency, low pass filter. That happens. That is more or less the same with these bubbles and in underwater sound. There is a similar trend that high frequencies are more attenuated.
Yes, and it's there's viscous losses in seawater or in water in general, but then in seawater we also have chemical losses.
Okay.
We see that kind of, like I mentioned, we don't have good signal level above 50 kilohertz, and that's also a function of the source we use. So the source level falls off pretty rapidly above 50 kilohertz. So that's one of the reasons we don't hear it. And we really see the highest loss from the bubbles themselves between 10 and 20.
Okay. Okay. Let's see if we have other questions. Either Felipe or Yvonne. I don't see any more. I think perhaps something else. No. Felipe, ¿no tienes ninguna pregunta? Okay, it seems there are no more questions. And let me see here. Felipe says no questions. Perhaps Yvonne. Okay, it seems we do not have any more questions. Let me think, perhaps something else that was in my mind when I listened to you. So these seagrass meadows, you mentioned that they have an important role in carbon dioxide. Here we have a question from Brian. Does water contamination affect the measurements? Water contamination?
So like particulates in the water, but we're not,
Yes.
yeah. Um, to some extent, but the kind of the seagrass are like such a dominant effect on the transmission loss in this case, like some small fluctuation we might see from changes in water quality, we're not necessarily acoustically sensitive to, but the seagrasses are very sensitive to changes in water quality, especially if the water becomes more turbid and less light can get to the seagrass leaves. That affects their ability to photosynthesize. And so seagrasses are sometimes called sentinel species because when water quality shifts, since they're so sensitive to it, they'll be like the first thing to die off. And then other things living in the environment that are also affected by water quality, you'll see their response, further down the line.
Okay, I do have another question about the regression models you found, which are good for estimating their the independent. There were two regression models, if I
Yep.
recall correctly. The independent variable was transmission loss, if I
Mhm.
recall, and the independents were, in one case, was it bubble production? What was the independent variable?
The other case, we were trying to estimate how much biomass that was there. And
Okay,
one reason that that's valuable, I mean, we can go out and like look with our eyes and see, oh, there's more or less biomass. The way people do it also is they collect the cores, like I said, that we use for our ground truth. But I don't remember if you could recall, I should have pointed it out when I show the figure, but sometimes the cores, collected on the same day vary by almost an order of magnitude. And so you're taking like point measurements with the cores, and the seagrass can be patchy and it can be like a little more over here and a little less over there. So you get this like variable measurement, and so it's really hard to see the progression over time. Actually, I think I would like to show that slide again if I
yeah,
may.
sure.
Because one thing that we get out of the acoustics is this time spatial averaging, which is very helpful here. So you see how we've got this like, nice, like if you look at the core data, they kind of like come up and they go down and then they're like highly variable. We've got huge error bars on these guys. Whereas like the blue line, this like darker solid blue line on here is what we're using for the
We're not
regression.
seeing your presentation, Megan. We're not seeing
Oh,
the.
so sorry. Let me try to share my screen.
Yeah, now I see it.
Okay, thank you. So the cores are the orange stars. So you can see like, for a single day here at the end of June, we have like a core that had, about a little less than 200 and another one that had more than 500. So, twice as much biomass in one core to the next. And you can also see these fluctuations where they're kind of being low and then they pop up and they go back down. So there's just a lot of variability in these point measurements that we get from the cores. And that's just a really natural thing. We see that in the published core data from many seagrass experiments. And that thing, if I point to the 22 data, just because it's a little less cluttered, you can see that there's this nice like seasonal rise in biomass in the spring. It kind of plateaus a little bit. And then you see this decay in the seagrass biomass, which occurs over a longer period. So kind of get about 2 months of growth, maybe a month or two of kind of healthy, fine growth for a while. and then almost a 4-month decay where it kind of dies off. And I don't know that you can clearly see that in the core data just because they're a lot more discrete in time, and they're also just have much bigger error bars and much more fluctuations.
Yes, but now I see that the regression model was the independent variable was a transmission loss, which you can measure and then estimate the biomass out of it. Were the coefficient of determination of these regression models, they were like tight or more or less the
So
the R squared?
I took the above ground biomass, which is the kind of our ground truth measurement, and then plotted them um, versus the transmission loss data for the day that it was collected, and just did the regression based on that. So the
Okay.
predicted biomass as a function over the 2 years has the same shape of that blue line, but then it has the biomass that goes between about 50 to 300 or 500 grams per meter cubed.
Okay, great. Well, let's see if we have anything else in the Q&A chat. Any more? Antonio Curie, maybe he wants to ask a question. We have here Megan. Okay. Well, I think there are no more questions, and I really want to thank you, Megan, for this wonderful presentation. Thank you very much for sharing your research with us. I know it's very important to have. We typically have more architectural acoustic presentations, but we find in our committee that we want this diversity of topics in acoustics because you never know, there might be a student that might take your path and become an underwater acoustics expert. So here there's another. How much can the sound from the sea affect? I mean, do you mean like um, I think perhaps the wind or the all storms? ¿Es eso, Brian, el ruido del mar, el- las olas o las tormentas? ¿Eso es lo que quiere decir? Okay, yes, in general. So the noise from the sea, I mean, I think the waves or the and then the human also, I mean, I think you mentioned ships or vehicles that are man-made sound sources.
So for the transmission loss measurements, we look at the signal to noise ratio, and then we calculate how much transmission loss we have. We only calculate transmission loss when we can detect the signal. And for that receiver that I used for the plots that I showed today, most of the time we have signal level that's greater than the noise level, so it's not a problem. For the ambient sound, I talked a little bit how we have some wind and waves, and I showed that time where you could see the rain come down. That clustering analysis is what we're using to really pull out the different frequency. So from that like frequency dependence, if you look at how that occurs, there's like a frequency signature of bubble production that's a little bit different from the frequency signature of wind and waves. So that's one tool we're using to kind of discriminate those in that way. And then we don't have a lot of vessel traffic in the data. And one reason for this is the seagrass meadow is so attenuating. They've been described as like libraries for the fishes because they're so quiet because of all the sound attenuation from the seagrass. And so, for example, like dolphins that want to like find fish to eat. It's very difficult for them to do that in seagrass meadows because the fish can hide so well too, because the um, active sonar pulses that come from the dolphins, like they use echolocation to find the fishes. The seagrass really complicates that process for them. Seagrasses are also make things like mine hunting difficult because of all the attenuation you get from the signals, and they block the targets really well. So yeah, it's a really interesting acoustic environment to work in.
So Brian, thank you very much. Very interesting. Brian asks, what type of filtering do you use to normalize the measurements? I don't know exactly.
So we're using an inverse filter to to pulse compress the um, chirps that we send. So it's an exponential chirp, and then we're using an inverse filter. It was actually really developed in the architectural acoustics lit.
I know.
Okay, yes, it's interesting because our underwater acoustics reviewers are unfamiliar with this kind of inverse chirp type of processing. Um, we also send like 5 chirps and then take the median level between them. So we've
It's
done a
like
lot.
synchronous averaging. Synchronous averaging.
Mhm. Actually, we're doing step averaging and power afterwards because there's so much variation from pulse to pulse because
Yeah.
we've moved too much for it to be uh, the coherent averaging actually makes the signal level worse.
It's not a time invariant system.
That's right. Not it's not time invariant.
Well, he says, thank you, great presentation. And I say the same. So, well, I think we will end here. Well, thank you so much, Megan, for sharing all this research with us. And well, I would like to say hello to all the people who will be watching this over the YouTube, and well, stay tuned to our presentations. Thank you very much, Megan.
Thank you.
Goodbye. Thank you so much. Goodbye.